Out of nearly 6,000 planets confirmed beyond our solar system, almost every single one was discovered indirectly, detected through a shadow, a wobble, or a tiny dip in starlight, never actually seen with a telescope's own eyes. Then, in the summer of 2025, that changed. Astronomers pointed the James Webb Space Telescope at a young star, and for the first time in the mission's entire history, actually captured a direct photograph of a brand new planet nobody had ever detected before by any method at all. We are talking about TWA-7b, and the genuinely historic moment when James Webb finally saw a planet, rather than simply inferring one existed through indirect measurement. If you have never thought much about the difference between detecting a planet and actually seeing it, stick around, because that distinction turns out to matter enormously, and this discovery represents a real turning point in how astronomers search for worlds beyond our own. Let's start with why direct imaging of exoplanets is so difficult in the first place, because understanding that challenge makes this discovery genuinely impressive rather than simply another entry in an ever-growing catalog. The overwhelming majority of the nearly 6,000 confirmed exoplanets discovered so far have been found using indirect methods. The most common approach, called the transit method, involves watching for a tiny telltale dip in a star's brightness whenever an orbiting planet happens to pass directly in front of it from our point of view. Another common technique tracks subtle wobbles in a star's position caused by the gravitational tug of an orbiting planet pulling on it ever so slightly. Both methods are powerful, but neither one actually involves seeing the planet itself. They simply detect the planet's influence on its host star. Direct imaging, actually capturing a photograph of the planet itself, is dramatically harder to accomplish, for a reason that comes down to simple physics. According to Anne-Marie Lagrange, an astrophysicist at the French National Center for Scientific Research, who led the research team behind this discovery, the fundamental problem is straightforward. The star is extremely bright, and the planet sitting near it is extremely faint. Attempting to photograph a planet directly is a bit like trying to spot a firefly hovering right next to a lighthouse beam. The overwhelming brightness of the star simply drowns out any light reflecting off a nearby planet. Before we go further, if this kind of genuine astronomical first excites you, go ahead and tap that like button right now. It really does help this video reach more people who appreciate watching real scientific history happen. To solve that problem, Lagrange's team relied on a specialized instrument called a coronagraph, specifically a French-built coronagraph installed on Webb's mid-infrared instrument known as MIRI. A coronagraph works by physically blocking out the overwhelming glare from a star's light, similar in concept to holding your hand up to block direct sunlight so you can see something faint sitting nearby. Even after using the coronagraph to suppress most of the star's blinding light, some glare inevitably still leaks through. Researchers then applied advanced image processing techniques to subtract that remaining unwanted light entirely, finally revealing a faint, previously unknown infrared source hiding within the data. That faint source turned out to be a planet orbiting a young star called TWA-7, located roughly 111 light-years from Earth in the southern constellation Antlia. Webb's observation revealed the planet sitting within a debris disk surrounding its host star, a vast, ring-shaped collection of dust and small rocky material left over from the star's relatively recent formation. According to the research published on June 25, 2025, in the prestigious journal Nature, this newly discovered world, designated TWA-7b, has a mass roughly similar to Saturn, making it the lightest exoplanet ever successfully captured, using direct imaging up to that point. If you are new here and enjoy watching genuine scientific firsts unfold in something close to real time, now would be a great time to hit that subscribe button, because there's a lot more of this waiting for you. That specific detail, being the lightest planet ever directly imaged, matters far more than it might initially sound. Every previous direct imaging success in the history of astronomy had involved discovering considerably larger, considerably brighter planets, massive gas giants, many times heavier than Jupiter. Objects bright enough that older telescopes could occasionally spot them despite the overwhelming glare of their host stars. TWA-7b, by comparison, weighs in at roughly the mass of Saturn, dramatically lighter than anything previously captured this way. Successfully imaging a planet this comparatively small and faint represents a genuine leap forward in sensitivity, demonstrating that Webb's instruments are now capable of directly detecting worlds considerably closer in scale to the rocky, potentially habitable planets astronomers ultimately hope to study using this exact same technique someday. TWA-7 itself makes for a particularly valuable target for this kind of research. It is what astronomers classify as a T-Tauri star, a very young, still-forming star that has not yet fully settled into a stable, mature phase of its life. Young systems like this one are especially useful for studying planet formation. because their surrounding debris disks still contain visible evidence of the raw material planets are actively assembled from, offering astronomers a genuinely valuable snapshot of a planetary system caught in the relatively early stages of its overall development. What makes this discovery particularly significant for the broader field of astronomy is what it represents about Webb's future potential, rather than simply this one specific planet. Until this observation, James Webb had already helped characterize more than 100 previously known exoplanets, using its powerful infrared instruments to study their atmospheres, temperatures, and chemical compositions in extraordinary detail. But in every one of those earlier cases, the planet itself had already been discovered years earlier using indirect methods, and Webb was simply providing additional detail about a world astronomers already knew existed. TWA 7b represents something categorically different a planet Webb itself actually found through direct visual observation rather than one it was merely following up on. Researchers involved in this discovery have expressed genuine excitement about what this success suggests for future observations. Orrin Carter, a postdoctoral researcher at the University of California, Santa Cruz, who helped analyze the Webb images involved in a separate, related direct imaging success, noted that this really represents just the beginning, with many more images of exoplanets expected in the years ahead, images that will meaningfully shape scientific understanding of planetary physics, chemistry, and formation. Carter also raised an intriguing possibility worth sitting with, that the same direct imaging approach could eventually reveal entirely unknown planets that indirect detection methods have simply never managed to catch. Worlds hiding in plain sight around stars. Astronomers have already studied extensively using other techniques. This discovery joins a small but rapidly growing gallery of directly imaged worlds that Webb has helped capture since becoming operational. Its very first direct exoplanet image, captured back in 2022, showed HIP 6-426b, a considerably more massive gas giant, roughly 6 to 12 times the mass of Jupiter, located about 385 light-years from Earth. Comparing that earlier image against the more recent TWA 7b discovery reveals just how quickly Webb's direct imaging capabilities have improved in a relatively short span of time, moving from detecting only the largest, brightest possible targets toward increasingly smaller, fainter, and ultimately more Earth-like worlds. Webb has continued pushing this frontier even further since TWA 7b's discovery. By 2026, astronomers had used the telescope to directly study the surface of a rocky exoplanet for the first time, examining a so-called super-Earth called LHS 3844b, located nearly 50 light-years away, revealing a dark, airless world that researchers described as bearing a strong resemblance to the planet Mercury. Rather than focusing on an atmosphere, which most planets lack entirely, this particular study examined heat radiating directly from the planet's bare rocky surface, representing yet another genuinely new technique for studying distant worlds that Webb has helped pioneer. Taken together, these achievements paint a picture of a telescope that continues to expand what astronomers consider possible, one careful, painstaking observation at a time. Direct imaging remains an extraordinarily difficult technique, requiring precise instrumentation, careful data processing, and often multiple follow-up observations before a candidate detection can be fully confirmed. But each successful discovery, from AIP 65426b's massive gas giant profile to TWA 7b's comparatively delicate Saturn mass signature, pushes the boundary of what Webb's instruments are capable of detecting just a little further, inching steadily closer toward the ultimate long-term goal shared across much of modern exoplanet research, directly photographing a genuinely Earth-sized, potentially habitable world orbiting a distant star. It also helps to understand exactly what kind of information direct imaging can reveal that indirect detection methods simply cannot provide. When astronomers detect a planet through the transit method or through tracking a star's wobble, they can calculate useful properties like the planet's approximate size, mass, and orbital period, but they never actually observe light coming directly from the planet itself. Direct imaging changes that completely, allowing researchers to study the planet's own light. In this case, Webb captured the actual thermal infrared glow radiating from TWA 7b itself. That distinction matters enormously for future research, because light coming directly from a planet carries information about its atmosphere, its temperature, and its overall composition that indirect methods can only estimate indirectly, if they can access that information at all. This is exactly why researchers place such enormous scientific value on developing and refining direct imaging techniques despite how technically difficult and resource-intensive the process remains. Every successful direct image adds a new data point to a rapidly growing catalog of planets astronomers can study using spectroscopy, splitting a planet's own captured light into its component wavelengths to identify specific molecules present in its atmosphere. For Planets discovered only through indirect methods. This kind of detailed atmospheric study requires waiting for the rare, precisely timed moment when the planet passes in front of or behind its host star. A limitation direct imaging avoids entirely, since researchers can potentially study a directly imaged planet's light, more or less, whenever the telescope happens to be pointed in the right direction. There is also something worth appreciating about the international, collaborative nature of this specific discovery: the coronagraph. Instrument responsible for enabling this observation was specifically built and contributed by French researchers, reflecting the broader pattern of international cooperation that has defined the James Webb Space Telescope project since its earliest planning stages. Webb itself represents a partnership between NASA, the European Space Agency, and the Canadian Space Agency, with individual instruments and components contributed by research teams and institutions spread across multiple countries. This particular discovery, led by a French research team using French-built hardware, installed on an American-led telescope, exemplifies exactly the kind of collaborative, multinational effort that has become increasingly standard for the most ambitious astronomical projects currently underway anywhere in the world. That international collaboration extends into how this kind of research actually gets validated and confirmed as well, because TWA-7b represents a genuinely novel discovery. Rather than a follow-up study of an already confirmed planet, researchers have been appropriately careful about confirming their findings before declaring the detection fully certain. Additional observations, ideally, capturing the same faint infrared source using different instruments or during different observing sessions, help rule out the possibility that a detection like this one might represent a background object, an instrumental artifact, or some other source of confusion rather than a genuine planet. This kind of careful, methodical confirmation process is standard practice throughout observational astronomy, and it reflects the same rigorous scientific standards that have made peer-reviewed publications, like the one describing TWA-7b's discovery, so trusted within the broader scientific community. If this story left you appreciating just how much careful engineering and patient science goes into actually seeing something as small and faint as a distant planet, make sure you are subscribed with notifications turned on, because James Webb's direct imaging program is still in its early days, and there is a very good chance the next planet it manages to photograph pushes this remarkable technique even further than anyone currently expects. This progression also connects directly to one of the most ambitious long-term goals shared across the entire field of exoplanet research, eventually finding and directly studying a truly Earth-like planet orbiting within another star's habitable zone. Every incremental improvement in direct imaging sensitivity, from CHIPI 65426b's massive gas giant profile in 2022 to TWA-7b's considerably lighter Saturn mass detection in 2025, represents real, measurable progress toward that much larger, more consequential goal. Scientists generally do not expect to leap directly from imaging gas giants to imaging small, rocky, Earth-sized worlds in a single dramatic step. Instead, the field advances gradually, refining coronagraph technology, improving image processing techniques, and steadily pushing the boundary of what counts as detectable, one increasingly challenging target at a time. Future missions currently in various stages of planning aim to push this capability even further. NASA's upcoming Habitable Worlds Observatory, still in relatively early planning stages, has been specifically designed with the long-term goal of directly imaging Earth-sized planets around nearby sun-like stars, searching for potential biosignatures, chemical signs that could indicate the presence of life. Webb's success with TWA-7b, however modest it might seem compared to that eventual, more ambitious goal, represents a genuinely important proof of concept, demonstrating that the underlying techniques required for that kind of future mission are already capable of producing real, scientifically validated results, using instruments currently in operation today, right now, this year, rather than remaining a distant theoretical possibility for some future decade. Using exactly the same careful combination of coronagraph technology and patient image processing, the same basic approach that turned a faint smudge of infrared light around a distant young star into humanity's latest confirmed member of the growing family of worlds beyond our own solar system, and quite possibly a small preview of exactly what it will eventually take to finally spot a true Earth twin somewhere. Out among the stars, closer to home than most people currently realize, waiting patiently in the data for the right telescope and the right careful eye to finally notice it.